live? Are we here? Hello? Okay, so welcome. Hello, hello. Good evening. So, we're here. Holy smokes, man. Whew. My brain, my mind. So we'll stream for about an hour and a half, then go to bed. Been doing a lot of thinking lately. Holy smokes, I couldn't describe how much thinking I've been doing lately. Jeez. Oh. A lot to think about, a lot to consider. Whew. Excuse me. So anyway, let's I need to work on programming problems in order to keep myself sane. Because my mind just goes to so many different places so very quickly. So what I'm describing, by the way, you might be wondering, like, well, what are you talking about? It suddenly occurred to me that I will probably end up with more money than I'll ever know what to do with. And I thought that I wanted to leave New York because it's really high taxes, I don't agree with the politics, and it's expensive. And then it occurred to me, like, well, actually, if I end up making like $1 billion, which I was just doing the math, it's like, yeah, no, I can make a lot of money. Something I was thinking about putting together, and the numbers are like, yeah, it would take you about 2 years and you're a billionaire. It's like, oh, okay. It's like, right, I'm a billionaire in 2 years. I'm not sure I care about anything after that, really. Thinking about it. It's like, yeah, no, that's pretty good. That's not bad. Probably end up a billionaire in a few years and a trillionaire by the time I'm dead. Doing it a certain way. It's like, what do you even do? What do you even do in that situation? Holy smokes. What do I even do? I don't know. With that kind of money, you can make anywhere comfortable. I don't even know what I'm going to do. I don't know. Property where I live is like $80 million. There was 10 acres going for $80 million. Buy a lot more than just that. 80 million. Excuse me, a lot more than just 10 acres with a few billion. Buy a bunch of these properties. Just hang out. I mean, what do I even care about anymore with all that? I want to have a family, I want to have kids, I want to do the thing. But I'm like, I don't even know what to do anymore. I'm like, no, seriously, so consider that. If you don't have to work at all, literally anything and everything you want, you just bounds of your imagination is the only bounds you have to deal with. Makes my head hurt. Dude, the world is way too much. Too much. I'm thinking, what is it? The book of Job. It's like the book of Job is tempt Job to disgrace God and defame God by taking everything from him. Maybe I'm the other one. tempt you to disgrace God, defame God by giving you everything, the whole world, on a silver platter, so you forget about God. Oh, this is ridiculous. This is ridiculous. This is absolutely ridiculous. This is ridiculous. I can't. What? This is absurd in a way that I can't even fathom. Needless to say, I'm having a hard time focusing on anything else because my brain is just turning to mush. Think about this stuff. Because originally the plan was like, okay, I gotta go interview, and I gotta get another job, and I gotta do this, and I gotta do that. It's like, you don't have to do any of that. No. No, sir. Not necessary. Not as necessary as you think, or at least you thought. No. Not at all. Not even remotely. Not even close. I don't know. I really don't know. I guess I'll work on putting together a website. I guess I could just wait for the money to flow in, and then once I'm there, I could just buy some property in New York in a nice neighborhood and have my wife come to me, right? Instead of, I was gonna go to the middle of nowhere and build a home, but might as well just stay in New York and try to make things as good as I possibly can, improve things. Don't send my kid to any public. I think I'll probably want to homeschool my kid anyway. Forget public school or even private schools. Yeah, just homeschool all the way, even if it's in a suburban kind of suburban area, something like that. Probably would want to prefer like a suburban area. Shoot, man. I don't even know. I really don't know. It's so weird. It's like, I don't know what to think anymore. I really don't. I don't even know. It's surreal. It's bizarre. It's crazy. Yeah. Huh. Wow. Oh, and not to mention, once I've got that property, I can just, raise food there too while I'm at it. Talked about that, It won't even matter. I won't need to do that. I mean, I haven't talked about it publicly, at least not much or not yet, but there are a bunch of billionaires here in New York and Washington, New York and DC that are, they need to be sort of ousted because they're going around destroying parts of the economy for their own gain. And basically, once I put them out of business, so to speak, put them in their place, not that I intend to get rid of them, but I intend to get rid of them, but I don't mean to get rid of them in any way that's, what's the word? Illegal or immoral, right? Effectively, I would buy them out, these guys. But yeah, actually, if you just care for the economy, then there's no reason to fear like starvation or anything, really anything. There's really nothing to be afraid of. It's like, oh, okay. What am I even doing anymore then? I don't know. I don't know. Hmm. Hmm. Sorry, I mean, it's a lot. It's a lot to think about. I also have this bad habit of not really sitting down and thinking about anything while I have time. Like, I only do it when I come online here, and otherwise I'm like, oh, let me go, like, entertain myself with something. It's very silly. But yeah, I don't even know anymore, man. It's really like, I actually don't care that much. I was thinking I should work remotely and find a wife and do these things, but actually, it's like I don't even really need to waste my time with all this other stuff because I could just make a ridiculous sum of money and then, I don't know, whatever I need, I can just buy. Okay. Okay. I guess I'm doing that. Yeah. There's a bunch of projects I like to work on here in New York. There are a bunch of infrastructure changes I like to make. I like to help people out and stuff, you know. Could spend them plenty of projects here worth a few $1 billion that I could spend the money on. There's plenty of stuff. I wouldn't feel guilty at all, feeling like I, you know, made a whole lot of money and didn't really have to lift a finger on any kind of real work. You know, all I did was do a little bit of math and realize couple truths about the market that can be not exploited, but you can use to actually they present opportunity. It's really just sort of the ignorance of the masses, their own choices. Like, it's really that blunt. It's like, why would you give away your money? it's kind of what it comes down to. It's like, why would you do that? It's like, well, because they don't know what they're doing. Not so much their money, but why would they give away their time like that? They don't have what do they call that? They don't have the foresight to know what they're doing. They don't know what they're doing. That's it. They just don't. They're ignorant. There is a quote from the Bible about, you know, if it's unprofitable, the man that's profitable will be given more, and the man that's unprofitable, all will be taken from him. Not all, but more will be taken from him. There's your quote for capitalism from the Bible, and that's definitely how I feel when I look at it, when I think about it. Position I'm going to end up finding myself in the next few years. That was ridiculous, man. I guess it is what it is. I don't know what you're going to do. This is how God created the world. Okay. Fair enough. Fair enough. By the way, those of you wondering why I'm suddenly thinking about all this, I was down like $500 in the market and I made $600 one day. Like, if I make the amount of money that I've been making the past, like, few months, yeah, I'll be like a billionaire in like a couple of years. It's like, this is a little ridiculous. It's a little ridiculous. Anyway, to return to what we were doing. So, Veach, please. Hard circuit design. Create a function which accepts it. All right, so we already talked about this like sort of at length. This is Karnaugh Maps, which Karnaugh Maps are used as a heuristic for circuit minimization. And oh no. And circuit minimization is at least as hard as NP complete. I think it's proven to be harder than that. This is non-polynomial, so it's rather involved. And actually, the problem that we ran into. So I'll describe how I solved this. So K-Maps represent a heuristic that you can use to solve the problem efficiently using your eyes, right? Using the human mind. Otherwise, it's an incredibly complicated problem for like a program to solve. And on top of that, I couldn't even program a solution that was fast enough to solve this. What we're going to do is we're going to go over my solution. I've been at this for like days. We're going to go over my solution, and then we're going to go over other solutions that other people have presented. Right, so there we go. Got it. Done. Solved it. I wrote a correct solution that timed out, and then I said, okay, it's too complicated to solve this efficiently. It's proven, and it's also not just too complicated to be solved efficiently. It's also too difficult for me to solve at least efficiently enough for these test cases. So I will also have to employ a heuristic, which is what I did. So yeah, it's pretty funny. I went through all this effort and I wrote a pretty involved algorithm that was correct but extremely expensive in terms of time. Took like minutes. Took a minute and 15 seconds to execute on these 9 test cases. And I don't know what the time bound is, but it's not a minute. A minute's too much time. But yeah, it was very inefficient but correct. And then I said, all right, I need something that'll solve these test cases, but also be efficient enough to run within the time bound, and obviously not be totally correct, because we know it's extremely expensive to write a totally correct algorithm. So I said, we'll use a heuristic then. So I used something that's sort of like the K-Map Heuristic, and it goes like this. I'll show you what it looks like. So what we start with is we say, okay, these are some base cases type of thing, just if you, what do they call that? It's a little bit of, I guess, error checking kind of a deal. And what we do is we get our set of upper letters as symbols, a set of lower letters as symbols, right? So we want these letters to work with. Then we get the number of symbols that we're going to be working with in the conjunctions. We'll call them the disjunction of conjunctions. We want to know how many of these they're going to be. So it looks like there's 4 here, right? So this figures out how many there are. We build this symbol map out of these upper letters and lower letters. We basically want to say, okay, given a 0 or 1 and a position, we're going to either give a capital letter or a lowercase letter, and the index will give us the correct, will identify the letter, and then the 0 or 1 is going to identify if it's capital or lowercase. So that's what this is. This creates a zip map. This creates a map that you can just give it an index and a 0 or a 1, and it will return you the symbol that you're looking for. We have another function routine to pad left. We're going to use this when we generate Boolean vectors or vectors of Booleans. This will just take a sequence, or any kind of, it could be a string or a sequence. A string can be interpreted as a sequence. In Clojure it is. And we're going to pad to the left elements from another padding sequence, which you could just give a repeating sequence, and that works nicely as well. And then there's a certain width. That is, the result will be at least that width. Obviously, if the string sequence you give is larger than that width, then this is irrelevant, but you won't have any padding if you do that. So yeah, that's a simple routine to pad the left side of a sequence. Then we generate Boolean vectors. We say basically what we're going to do is take excuse me, all of the integers up to and excluding this n, right? Not including the n, but 0 to n excluding n, or 0 to n minus 1 inclusive. All those integers, convert them to the binary representation as a string of those. So convert the integer to a string, get the binary representation of that as a string, and then we're going to pad that string with zeros on the left side until we reach this input number of bits. So we would probably want, so we like if we wanted 4 bits, obviously if you get a 0, then 0 converted to binary is just 0, and you convert that to like a sequence of strings, it's just sequence of characters is just 0. So you want to add 3 more zeros, and so we pad with with characters, right? So you have 0 characters representing 0 would be repeated and padded. And then what we do is we map all those characters, the character sequence, to an integer sequence of zeros and ones. So we would, by subtracting the 0 from by subtracting the ASCII integer that represents the 0 character, right? So we would have like, maybe, for 0 you might have 4 zeros characters converted to integers. Those might be, I don't know, some number, and then we subtract that number off, and then that makes it, we end up with 0 after that, for that sequence. And then finally convert what we've got to a vector. So now we get a vector of 0, zeros and ones, and this whole routine, we map that over that range. So you can generate, 0, 0, 0. So if it was like 2 bits, and we want to go from 0 to 4, right? Not including 4, but so it'd be 0 to 3 inclusive. You'd have 0, 0, you'd have 0, 1, you'd have 1, 0, and 1, 1. Right? You'd end up with all 4 of those as vectors. So you get that. Okay, so you got a routine that does that. Great. Next, you want to generate these K-Map matchers, they're called, or I decided to call them. The idea behind this is what you've got is a situation where you can use you can generate a bunch of Boolean vectors for all of these bits, right? And then consider each of those Boolean vectors separately and say, okay, and that's actually what this does, this K-Map matchers. It's going to generate, it's going to consider a single Boolean vector, and you can consider something like 1, 0, 1, 0, right? And what we're going to do is we're going to say, okay, the ones will represent the unchanging portion of our conjunctions, and the changing portion will be the zeros. So we actually effectively split up the we sort of partition into 2 pieces our what do they call that? Our Boolean variables. And what that's going to do, it's going to mean is the ones that are unchanging will be constant throughout the conjunctions that we're going to generate, and the changing ones will cycle through all of the possibilities. So as an example, all of the possibilities where you keep A, B, and C unchanging as lowercase values, you would have a group of A, B, C, D, lowercase d, and then the same A, B, C with capital D, right? And that would be a grouping of 2 conjunctions, a disjunction of 2 conjunctions, where the unchanging bits, so that would be like 1, 1, 1, 0, would be unchanged, and the changing bits would be would change for that particular group. Now, what's interesting about this is you may realize very quickly that, wait a minute, 111 should be all capital ABC. So you should really have ABC all capital and then capital D and then ABC all capital and then lowercase d. And you should have a group there. Well, that's actually what this handles. Is this actually if you think about it, you'll realize there's actually a whole sequence of unchanging elements as well. So for each of the unchanging elements, there are, so for instance, if we have 3 ones, we have 8 different possibilities for things that are unchanging. And then for each of those unchanging values, there's then this sequence of 2, so groups of 2 that you can append to that unchanging sequence to create these sort of subgroups. That's effectively what this is going to do with it. For a given Boolean vector, it's going to loop through all the possibilities for the different ones that you could have, and then for each of those possibilities, loop through all the possibilities for the different zeros you could have. And you end up with a total of 2 raised to the n, or 2 raised to the number of bits, which is, we have 4, right? So it would be 16. For each of these would be 16 groupings. It would be, 16 groupings total. Every time you end up with 16 groupings total. I think that's correct. And so all these different groupings are sort of K-Map matchers. They basically are equivalent to, in the Karnaugh map, there's a you can sort of circle a group of 4, powers of 2. You can sort of circle these groups of 2. Each of those groups of 2 represent what these matchers would represent, each of those groups. So basically you generate all these different possibilities. That's kind of what you end up doing. And now what you've got to do is say, all right, once you've generated all that, right, so this is the more code, we're going to generate the Boolean vectors for our particular case, right, because these are functions that we're defining. So we actually employ the function to get the generated Boolean vectors. Then we're going to say, okay, using those vectors, we're going to generate all these matchers, which amounts to, applying this function on every single Boolean vector that we just generated and concatenating all of the results. So now we have all those different groups for all the different possible sort of ones and zero combinations, all the different numbers, all the different groups that are generated by calling this function, right? And then now what we say is, okay, take that, filter out the ones that are, for the sake of efficiency, filter out the ones that are not subsets of the conjunctions that were given. Meaning, like, you only want to have these groups that are full, right? The only groups that you can use are full groups, not ones that have like some 0. In other words, you could have a group of 4, but there could be 2 zeros and 2 ones in there. We're not interested in that. We're only interested in the full groups. So things that are not subsets of the conjunctions that were given, we remove those, right, preemptively. That's what this filter does. Now notice also that there's a simplified and extracted. We want to keep track of, so that's also part of that. When we have the ones and the zeros, right? The extracted part is the total group of, or the total sort of conjunctions, like for instance lowercase abc, and then there's capital D, and then lowercase abc, and then a lowercase d. That group of conjunctions, there's 2 of them there. You can simplify that group of conjunctions to just lowercase abc, and you leave out the d because it doesn't matter what the d is, right? That's sort of the whole point of this exercise, is to figure out which portions of the logical circuit you don't need to consider. Circuit minimization, right? So there's a simplified form for that particular group of conjunctions. That's why I decided to call it simplified and extracted. So now we kind of pair those together in this. By the way, these matchers, they give you a list of 2 values, right? There's the simplified form and the quote unquote extracted form, which all these things are sets too. Also, there's sets of these symbols, and there's also employed somewhere in there when we're generating this stuff is you actually use that symbol map that we generated previously to take, instead of, you know, 'cause like I said, we're going to loop through for all the ones sort of indices. We're going to loop through all the different possibilities for the symbols. Well, we want to actually convert, you know, to real symbols. So we would take the indices and, you know, loop through all the possible zeros and ones you can have at those indices, and then retrieve the different symbols so you can sort of get the those sets that you're looking for. You get the sets that you're looking for. Right, so we end up generating our simplified as well as quote-unquote extracted, which is sort of all of the conjunctions in gory form, right, in total form. So then we get our matchers, we concatenate, right, and we get these K-Map matches, right. We filter out the ones we don't want. The what do they call that? Yeah, these filter out the ones that aren't subsets of the conjunctions that were given, and then we sort them. And the reason we wanted them sorted is we want to actually we're going to end up performing the Karnaugh Heuristic, right? Which is basically try to get the biggest chunks sort of circled off of the graph that you're looking at, of the picture, the biggest chunks circled off, and then optimize from there, which is exactly what I end up doing. So we want to sort to say, okay, give me like the largest sort of groupings first. We're going to go through those from largest to smallest. What this amounts to, though, is that you can also say the largest groupings correspond to the smallest simplified forms, so you could just sort by the simplified forms in ascending order, and that gives you also the sort of it gives you the same sort as sorting from the descending from the largest groupings to the smallest. So that's fine. So now we implement this greedy Karnaugh heuristic, which is just a this actually ends up being something I use in a reduction call, and this is as simple as you just loop from over all of the matches and try to apply as many of the as many as you can as soon as you can. So you apply the biggest ones, and they can overlap, and then once you've got a full set, once you've got everything accounted for, then you can just return, right? You just or you just repeatedly return the rest. Repeatedly return the same thing once you sort of fulfill the condition. I could have also used reduced here. I didn't think to do that, but this case is this would be the reduced case. I didn't think of that. That would have been a good idea as well. So right, so you perform the heuristic. And then the problem with the heuristic is it's actually incorrect, this one, initially. We've got to do a little bit of optimization afterwards. And the reason why this one is incorrect is what happens is you end up taking a bunch of stuff that isn't entirely necessary. I forget exactly what happens. It works like this. It works like there's 3 big pieces that overlap, and they don't get everything, but they all get something more. They all get something new that wasn't already grabbed yet, or wasn't already covered. And then when you add another piece that does cover what's left over, it actually covers the only piece that one of these 3 actually contributed. So you can remove one of the first 3 that you added, if that makes sense. That's why this heuristic was incorrect and is incorrect. It would add these 3 pieces, these 3 covers, and then once there's a piece, there's still one thing missing, so there's another piece that's covered. But once that piece is added, the only contribution, the only portion that was not already covered by the first 2 pieces you added, so the third piece that you add, the only portion that the third piece actually added to the equation was then covered by the fourth piece. So then you could remove the third piece. So obviously what I ended up doing was writing a heuristic, sort of a, what do they call that? What's that called? A cleanup routine for the greedy heuristic, because the greedy heuristic will actually give you too much in some cases. It'll give you too many. It could do what it did in this case and give you an extra piece. You can write a cleanup routine, which is a fixed point iteration, which does something as simple as, okay, if you have any after you've got this set of pieces that you're looking at that you know is a complete set and is relatively small but isn't necessarily what we're looking for, remove any pieces that you could determine are unnecessary. And that was what I ended up doing. So I wrote this routine. So you have this K-Map. This actually just takes the before you had a list of the simplified forms and the sort of extracted conjunctions. This just creates a hash map out of those things. So now you can go from the simplified form to the sort of set of conjunctions. Yeah, that's useful in the following routines. And then so I said, okay, here's the heuristic cover. Just apply this reduction to get the greedy cover, or the greedy version. And then there's another routine that just removes redundant pieces, which there was some finagling I had to do here. There was also some interesting kind of error messages from sort of outdated Clojure compiling. But yeah, that does a sort of as described. It'll look for any pieces that are redundant. Just loop through all the pieces that you have. Check to see if you were to remove that piece, would this thing still be complete? Would this still have cover all the conjunctions you're looking for? This is also where the map is useful, because you can go from the simplified set directly to all of the sort of resulting conjunction groupings that the simplified pieces represent, and then you can union all of them and see, okay, does that still cover what I'm looking for? If it doesn't, then obviously it's a necessary piece. If it does, then that piece you removed is unnecessary. And you just keep removing pieces until either remove or not remove, depending on if it's necessary or not necessary. And you go loop through all the pieces once, and if you yeah, that's actually it. You just loop through all the unnecessary pieces that you could determine immediately, remove them. And what this is going to do, the algorithm, so that's what that does. It just does one loop through the pieces you've got and tries one by one to remove it. And obviously once you've removed a piece, it'll continue with that new set with that piece removed. Because you maybe can remove a few pieces at the same time. Once that's removed, then you have the next thing, which is you're actually going to loop and use what's called, like I mentioned, a fixed point iteration, where you're going to keep trying to remove pieces until you hit an idempotent state, meaning you can't remove any more pieces that are redundant. You've removed all the redundant pieces from what your heuristic gave you. Once you hit that point, obviously you've got a minimal cover for what you started with, or rather not what you started with, but what you received from the heuristic. So that should take care of that edge case where you end up adding too many pieces because of just the order that you added the things in. Excuse me. Now this isn't necessarily a correct algorithm either. Anyway, even though it works on these test cases, it's not correct in the sense that it doesn't necessarily cover all of the sort of varying cases. Like it's not necessarily optimal. There's no reason to believe that this is optimal. It might be optimal, and I just don't realize it. I don't have a proof of it. But it's certainly not efficient, because all those routines that I described earlier with generating Boolean vectors, that is at least exponential. And the following routines after that are not exponential, but that's like at least exponential. And then these things are kind of efficient, just relatively efficient in comparison. But I don't think they guarantee you a minimal cover that you're looking for. I think it gives you something pretty good, and obviously good enough for these test cases, but does not give you I don't think it's minimal. I could be wrong about that. Maybe it is minimal and I just don't realize it. But yeah, that's the whole algorithm. Bit of a mouthful, bit of a doozy. 100 lines of code over here. Obviously, if you spent more time, you probably could find a way to sort of siphon this down, narrow it down, just kind of keep churning it over in your mind and improving, and you can sort of keep condensing this. And we'll look at some of the solutions for that. Some other folks probably did take the time to sort of condense this down, make it better, I guess. Better approach. 64 lines, 23 lines over here. It's pretty dang. 15 lines, holy smokes. Jeez. 30 lines. Yeah, I mean, other folks seem to have pretty much more succinct answers. Mind you, I didn't even know what to do. I think this is there's also another algorithm called the Quine-McCluskey, I think it's called. There's another heuristic here. Yeah, Quine-McCluskey algorithm, which is, if you see this one, find primes, that's the Quine-McCluskey algorithm, because there's another heuristic, right? There's that heuristic, which also does circuit minimization, and that has something to do with prime implicants, whatever that means. So there's even more involved code for that. Hacked functions together, yuck. Yeah. 15 lines, holy smokes. It's also another thing where it looks like the shorter lines of code only used small sets, I suppose. They assumed sort of smaller sets, which I guess you kind of need to, sort of. But yeah, I don't really want to read other people's code. I mean, I realize that they're probably just better for one reason or another. Yeah, naive implementation. Yeah, there's a lot of code you could save if you make certain assumptions. I guess, I don't know. Also, I don't know if these could also just be sort of optimized in terms of the number of lines and characters. Quine-McCluskey algorithms as well, which would be maybe potentially less involved than the one that I ended up writing. Or are they all Quine-McCluskey? Looks like a lot of people did that. Yeah, that's something, man. That's something, huh? I don't know. I don't even know what the Quine-McCluskey looks like, so I'm kind of skipping over a bunch of stuff. Namespace management, variables. That's interesting. Kind of like this. It's an interesting way of writing the code, documenting it. Makes it a lot more verbose, though. Also suddenly realized why it took so much time to load this page. Yeah, it's like 100 lines, not too bad, I guess, after all. There's some explanation, but let's look at 20 lines of code. I think these are, like I said, I think these are the residue stuff. I think these are Quine-McCluskey algorithms that have been sort of optimized in terms of the number of characters. And I mean, as mentioned, I think you can. I think that you can ponder this long enough to figure out how to optimize. I don't know what he did here, this guy. I don't know what he did. It's interesting though. Excuse me. I think this may also be Quine-McCluskey. I don't know. It's not like these necessarily some of them advertise it, but not like everybody advertises what they use for the algorithm. I wrote my own. I rolled my own, man. I freaking thought through something that would work, that might work. So, you know, whatever. I could have looked up an algorithm, but I thought of my own. Thought of my own, man. Anyway, moving on. So that's cool. Interesting question. I'm glad we read it. Glad it was asked. But definitely took a really long time, and in comparison to the other problems, other questions, definitely more interesting question. One of the more interesting ones. You know, extremely complicated problem, extremely complex problem. Pretty interesting bit of history with computer science, right? That was in the 50s that Karnaugh Maps were invented to help solve this problem, circuit minimization, which was a very real problem given in the 50s that they didn't have a whole lot of hardware resources. You know, today you can get all kinds of goodies rather cheaply, but back then was no such feat, not such an easy thing to do. Get yourself on get your hands on some nice hardware. Excuse me. So circuit minimization was a pretty important thing at the time. So yeah, all right. Let's go to the next problem. So 141. I think I already solved a bunch of these. Yeah, tricky card games. I think we went over that. I don't know if I did this on stream. I think I did already. Yeah, there was some like more efficient ways to do this. Some neat ways to do this that involved what did it involve? Involved its sorting. I think sorting the cards and using a little bit of destructuring, clever destructuring and some sorting. Yeah, it was neat. But I'm not gonna go over it again. I think. There's 142, 143 rather. Yeah, this one I was able to kind of sort out very quickly on stream as well, so that was good. And you just multiply and then add. 144. Oscill rate, I also thought I was proud of myself. I felt good about this solution because I thought it was clever. But you can use reductions over a cycle of the functions and just keep applying different functions to the value as desired. That's it. That's what this question is. It says oscillating iterate a function that takes an initial value and a variable number of functions. It should return a lazy sequence of the functions applied to the value in order, starting from the first function after it hits the end. So it'll go int double, int double, int double, keep applying to this value that you have, and then you want to return the whole sequence of starting with the initial value all the way, until you've got a, I guess, actually it's infinite, this sequence, but you only take so many. Right, and here's like subtract 3, add 5, and then here's one that increment, decrement, increment, decrement, increment, right? 0, 1, 0, 1, 0, 1, 2, 1, 2, 1, 2, 3, I guess 3, 2, 3, 2, 3, 4, 3, 4, 3, 4, 5, 3, 5, 5, 4, 5, 4, right, etc. It's pretty cool, pretty neat, pretty interesting. But yeah, just like simple one-liner here, using some of the built-ins from Clojure. 145 for the win. This is super simple. This one, they just kind of want to show off what the for semantics can do, the for syntax, and this is like a list comprehension, I guess is another way to look at it, think about it. But obviously this is just a sequence of this is just the sequence of elements that are less than or equal to 40 and also 1 modulo 4. So if you take the remainder after dividing by 4, you end up with 1. So that list is 1, 5, 9, 13, 17, 21, 25, 29, 33, 37 should be what you get. And then there's a few different ways to describe that list. So you can describe it here, say over the range, including the 0 to 39. When you divide by 4, if the remainder is 1, right? That you could describe the sequence that way. You could describe it as an iteration of adding 4 repeatedly, so 0, 4, 8, 12, etc., all the way to 40, to 40. And then define z to be those values plus 1, each of those plus 1, and then take all of those values while what you're looking for is less than 40, right? So obviously these are sort of the multiplications by 4, and then you just add 1 to each of those, starting with 0. So that gives you one modulo 4 as well. And finally, they do this partition of 2 over the range from 0 to 19, and then you add the two values, the ones that are one next to the other, add them together. The reason why this comes and gives you the same answer is because you can prove this by induction. So a partition is going to give you, this partition by 2 is going to give you groups of every 2. So 0, 1, 2, 3, 4, 5, 6, 7, etc., right, all the way across. And the proof by induction is basically, because 0, 1 works, you add 2 to get to the next set, right? So if it's 0, you add 2, and to 1, you add 2, right? So now you have to go from 1, 0, 1 to 2, 3, you have to add 2 to both values. Well, clearly that's equivalent if you're considering the sum of these values, that's equivalent to adding 4 to get you to the next sum, right? So going from the first set to the next set, you add 4. Well, that means that you're constantly adding 4, and as long as the first value is in the equivalence class of 1 modulo 4, then adding 4, all the resulting numbers after that will also be in the same equivalence class. So that means as long as the first thing you're adding together, which is 0, 1, which you can verify directly, is 1 mod 4, right? Then everything that you add after that will also be 1 mod 4. And we also need to show that this is the sort of to the left side, right? In other words, it's not just like 5 and then 5, 9, etc. you could technically have partitioned it that way, and the only issue is that you need to make sure that you're covering sort of all of the values modulo 4, 1 modulo 4 that you're interested in. And I guess you could just say something, you could make an argument something of like, you have to starting from 1, which is the beginning of the range, and then ending at 37, which is where you end up ending at. Then you've covered the entire, then you've got the entire sequence that you're looking for. Yeah, because the sequence you're looking for is continuous, is contiguous, is the contiguous elements of that equivalence relation. I'm not sure, it's kind of a hand-wavy proof of that, but sufficient, I think. So yeah, it's pretty cool. This is kind of a clever way to get an equivalent, not so obvious, kind of clever way to get an equivalent sequence. And finally, I said, okay, well, just give me to iterate over all the values from 0 to whatever infinitely, then take all the multiplicands, multiply those integers by 4 and add 1, and then only take the ones that are less than 40. And that's an equivalent way to write the sequence. You just compare that sequence to the other sequences, and you're done. Works out nicely. Very neat, very cool. 146 now. We've got trees into tables. This is kind of an interesting problem. This might have been the last problem I solved before I went home. So the idea is they say, okay, the for macro allows you to quote unquote walk over multiple sequences in a nested fashion. It's excellent for transforming all sorts of sequences. If you don't want a sequence as your final output, say you want a map, you're often still best off using for because you can produce a sequence and feed it into a map, for example. For this problem, your goal is to quote unquote flatten a map of hash maps. Oh, you know what I should do though? I forgot. I should actually look at the solutions that other people presented for this one. This one should be kind of interesting. Get a lot of different variations on this theme. So a good number of folks, oh, that's cool. I could have used this range. I didn't think of that. Set the step. Some folks just put the sequence in there directly. Some folks use a filter. Yeah, I thought it would be cute to just kind of define define the sequence in another way. Oh, cool. Okay. Partition 4, drop 1 range. Oh, that's interesting. The first of partition 4. Huh. That's another way to do it. I don't think I would have chosen that way, but it is another way. All right, because if you partition into groups of 4 and then take the first one, that sort of implies that each value will be separated by 4 elements. There'll be at least 3 elements between them. So a value of 4. Yeah. Kind of just, you know. All right. So people didn't get too clever with these. Folks didn't get too clever. So I don't know what the equals does. Clojure here. Yeah, okay. Anyway, let's go to 146. Trees into tables. Yeah, this part I am curious what other folks did. So it says, right, produce a sequence feed into a map, for example. If this example, your goal is to quote unquote flatten a map of hash maps. Each key in your output map should be the quote unquote path that you would have to take in the original map to get to a value. So for example, 1, 2, 3 should result in 1, 2, 3. You only need to flatten one level of maps. If one of the values is a map, just leave it alone. That is, get in original K1, K2 should be the same as get results K1, K2. So the deal with this is you have like hash maps of hash maps. You've nested hash map structure going on. And what they want to say is, okay, just flatten the first two keys of your nested structure. So here you have like A, which gives you a hash map of P to 1 and Q to 2, and then B gives you another hash map from M to 3 and N to 4. What you want to do is say, okay, given keys A and P as a vector, get the value there, right? That'll be our new hash map. And then also AQ gives you 2, AP gives you 1, BM gives you 3, BN gives you 4, right? And you can see the examples sort of what they do. And they say if it's a if the key itself is some kind of a structure, then just use that as well. Like don't sort of quote unquote destructure the key. So down here you have M is the map. Oh no, yeah, M is the key, then 1 is a key, and you get ABC. And then there's another M is a key and 3 is a key, and you get nil, right? So M1 is a vector, gives you ABC in the map, and then M3 is a vector, gives you nil. So that's what they're looking for. And I did this probably the correct way, I guess. I'm not entirely sure if it's right, if there's a better way. I mean, it's correct in the sense that it solves the test cases, but it's not like super succinct. So I said, okay, we'll use a for expression. We'll get the top level key of a top level key. We'll loop through the keys of the initial map, and then the next level key is going to be the keys, or loop through the keys of M given this other key, right? So we sort of doubly loop through. Which, by the way, when I was talking about the the changing and unchanging Boolean vectors, right? Processing the vector to get all of the possible groupings, the disjunctions of conjunctions. Does that make sense? I used a for loop nested within another for loop, not a for loop, and a for loop, a for function within another for function. So I did make use of this, a similar kind of thing here. And yeah, and so what you do is you say, okay, so loop through each of the keys at the top level, and then we're going to loop, given that key, we're going to get what's in the hash map there, and then get the keys of whatever's there, and we're going to associate each one of those with one of these, right? For each of those combinations, we're going to do the following: create this vector of two values, which is this top level key next to the next level key, right? Put these together into a pair, and then also process these key by key in the map first to get, so first the top level key to get presumably another map, and then the next level key to get what's in the map at that key, right? So this gets you your value, and this produces that vector of the two values. It's like, in some sense, extremely straightforward, right? And then as you can see, it does get what we want. And then, by the way, once you generate this thing in the for expression, push all of those pairs into a hash map, and this works nicely. So this will automatically destructure the pair into a key and a value in your hash map, so that it's usable after that point. So I do want to see what other people did, though, as a solution. I think other folks probably have a more clever way to do it than I did. Split map, using a reduction, reduce KV, reduction into, that's what I did. Although, not quite. I mean, mine was a little more involved than this. Oh, he destructured. Oh, I didn't think of that. Oh. He explicitly destructured. I didn't even think about that. I forgot you could even do that. So key value pair. So he didn't just get the keys, he got the key value pairs. Oh, and then he ignored these k, right? Because he only really cared about the v's. And then you got the value key value pairs. Right, so destructure here to get each key value pair at the top level, and then get for each of those values, get the key value here. But you still need this key, right? Oh, that's really interesting. That's so clever, the way that was done. That's extremely clever. I like that a lot. But yeah, I've also noticed a lot of the sort of, we'll call it code golfing that goes on, where you really reduce the code a lot, and simplify the code a lot, is making use of the destructuring. It's not really as phenomenal as you might think, I guess, not as sort of groundbreaking or earth-shattering. So yeah, obviously you could put this on one line to get this guy. Pretty sweet, pretty cool. I should make use of that. I like that. That's clever. KV and then VKVV. Very, very good. I like that a lot. All right. It's always if I'm willing, it's always what's the word? Fortuitous or fruitful to take a look at what other folks came up with. The clever guys. All right. What was that? 145, 146, 146. Yeah, 147. All right. Now we're caught up. Now we are where I left off. So this is an interesting question. Pascal's trapezoid. Write a function that, for any given input vector of numbers, returns an infinite lazy sequence of vectors, where each next one is constructed from the previous, following the rules used in Pascal's triangle. For example, 3, 1, 2, the next row is 3, 4, 3, 2. Beware of arithmetic overflow in Clojure since version 1.3 in 2011. If you use an arithmetic operator like plus and the result is too large to fit into a 64-bit integer, an exception is thrown. You can use plus quote to plus single quote to indicate that you would rather overflow into Clojure's slower arbitrary precision big int. Yeah, so we'll use big int addition, I think, because if you use 100 of these, right, the problem is this is what do they call that? This is exponential, Pascal's triangle. Right? Pascal's triangle represents, it's not Fibonacci, but it's, actually no, I think it is. One of the Fibonacci numbers is in there. Is that right? I'm not sure if that's true. I'm wondering if the Fibonacci sequence is in there somewhere. I don't think so. But anyway, it is exponential though. The size of these values, they get pretty large pretty quickly. Now what's interesting is I don't fully understand how we go from here to here. So if 312 becomes 3432, what do you add 312 to the right? So it's like if you append a 0 and then do 312 without the 0, add it across. You get 3, 4, 3, yeah, 2. Interesting. I think we can do can use a routine here. call this Pascal's trapezoid. All right. Now what we want to do is use this test case. I have an idea, but I'm not. I kind of want to code it out here first and test it. X's. I also like that convention to call it X's. Sequences you don't know what to call them. So we can do something like this, like conj x's with 0, and then take the rest of this, and then we can map this guy to x's, and then that's supposed to be a vector. I wonder what this will do. So what this does, it takes 232, makes it 2320, and then I think this is false. I don't think this works correctly. It creates 2320, then it gets 320 and adds that to 232. No, but there needs to be this first one here. How do we do that? That's a tricky thing I never quite got. I mean, you can cons, I suppose. Yeah, I mean, I guess it's fine. Yeah, all right, whatever. It's fine. Cons of the first of the x's. This should work, I think. Let's see what we get. False. Nice. Nice. No printing. Just, I don't know. Don't check if this is equal. Just display it. Okay, try again. So we take 232, we get the first, which gives us a 2. We cons this. Why is? Oh, no. What? Wait a minute. What? Huh? Huh? We go again. Alright, this doesn't make a lot of sense to me. 232. If we take the rest of 232, we get 2320, so we should get 320. So that's maybe something I'm wondering, like what are we actually ending up with here? What does this look like? What does this look like? What have we got here? 320, 232. If we map the sums, now that's super confusing because I thought this would give us a sequence. You know, I thought this would give us a sequence. What does this give us? Like maybe I'm just misunderstanding here what this does. No, that's what. Oh. Aha! That's why. Oh. Really? Huh. I think we're supposed to iterate to create the sequence. Yeah, they want to sequence these things. That's why second is what you... Oh, that makes sense. Okay, got it. Got it. So we want... okay, I think I understand now. So... Yeah, so this original thing, cons of the first of x, we do want that. And then create a vector out of this. Whew. Okay, let's take a look. Yeah, all right, that's what we want. Okay, understood. Understood. Had the right idea. Iterate. Function. You know, I don't know. X's. Let's call it initial. There we go. That's what we want. I don't want to do it. There's a few pieces there. It was like kind of. I wasn't really able to do it all in my head. Nice. Nice. Let's give this a shot here. There we go. There we go. Not too shabby. Not too bad. Not too bad. Solutions that the user you follow have submitted. So yeah, let's see what other folks did. I like this. I think this is pretty good, but I'm curious what other folks did that came up with. Lazy sequence, cons, map v. So, oh, I didn't think of that. Cons can join map v. And what does tr do? That's the function. Right. Right, lazy sequence gives you... You could iterate this though. Like it doesn't need to be... Yeah, that's what's done here. Concat. Yeah. Fair enough. That's more or less what I did. Not too far from what I did. Maybe it would have been a little bit better to think to do that, to do conj and cons, and then map v. It's fine though. That is a-okay. All right, moving on. So 1:48 now. All right. I got another 10 minutes here, and then I'll go to bed. We'll finish this off. Go to bed. Write a function which calculates the sum of all natural numbers under n, first argument, which are evenly divisible by at least one of a and b, second and third argument. Oh, that's interesting, the big divide. So they're evenly divisible by at least one of a and b. Oh, this is like a FizzBuzz question. Numbers a and b are guaranteed to be coprimes. Oh, this is a very interesting question. Actually, this is one of the questions that you'll get. This is one of the first questions on Project Euler. This might be the first question on Project Euler. And you can the most obvious solution will exceed the time limit. So they're asking for, oh, this is really cool. So they gave it a medium. This would, so all right, let me show you this. This is cool. I like this question. This is a good one. I like it because it's very clean. Okay. Multiples of 3 and 5. We list all the natural numbers below 10 that are multiples of 3 or 5. We get 3, 5, 6, 9, and 9. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1,000. So this is the first problem on Project Euler. this is considered sort of the easiest problem on the site. Very good introduction question. Very similar to like what's called FizzBuzz, which basically FizzBuzz is you print for the first, let's call it n numbers, or first 100 numbers, 0 to 100 or 0 to whatever, some range. If the number is, you print the number, or if it's a multiple of 3, you print the number. You do it this way. If it's a multiple of 3, print fizz. If it's a multiple of 5, print buzz. And if it's a multiple of 3 and 5, print fizzbuzz. And everything else, just print the number itself, right? That's fizzbuzz. That's like I think Joel Spolsky was talking about how programmers, when he interviews programmers, there's so many programmers that don't know how to just program something really simple, which I thought was kind of interesting, but apparently that's a thing. So anyway, that's fizzbuzz is just when you're interviewing folks, that basically helps you to sort out whether or not the person you're dealing with has actually ever written any code in their life at all. This is very similar. Instead of printing out fizzbuzz, you're going to add all the only those numbers, right? And you're also going to but this is a little bit special. So the reason why they give this one medium rather than easy, this is like the easiest question, is because they're varying between 3 and 5, right? They're varying the A and B. In this case, 3 and 5 is fixed. It's very clear that they're coprime. Here, A and B are not fixed, and it's guaranteed to be coprime via the test cases, right? That they give you. And they also said they're going to give you very large n, so you've got to do something special. You can't just loop through all these numbers, as you probably would, if you're a beginner and this is sort of your first sort of toy problem that you're working on. You cannot simply just loop through all of the numbers given a very large n. So what you have is very interesting, but there's a more clever way to solve this problem using a little bit of set theory. And what you do is you say, okay, using a little bit of set theory and a little bit of number theory, you can write a very, very concise, very sort of elegant solution to this. And the way that it goes, if you're ready for this, is you say, okay, what you're going to do is you're going to count the multiples, right? So there's multiples of, so in this case they have 17 and 11, right? There's multiples of 17 and there's multiples of 11. Whatever number you have, if you divide by these values, right, these multiples, if you divide by that, then you can figure out how many such multiples exist, right, of each of those. So if you have 1,000, the multiples of 17 would be 1,000 divided by 17, and I believe it's the floor of that. You take the floor. So like 100 divided by 5, there should be, I think the floor plus 1. So 100 divided by 5, there'll be, 0 or 0 to 100. It does matter natural numbers, right? So never mind. So you don't need to add 1. I was going to say 0 is divisible by everything. So if you're using natural numbers and not including 0, then you can say, yeah, so 1 to 200, if you divide by 5, that gives you the number of divisors, number of multiples of 5, right? Which should be, 200 divided by 5, I think is 40. So there'll be 40 of these, right? And the way that works is that you're going 5 plus 5 gives you 10, plus 5 gives you 15, right? You're adding 5 repeatedly to get up to 200, so then you divide, right, to go backwards in the other direction. The number of times that you've added to get to 200, dividing by that, dividing by 5 will then give you the number of times you had to add, which is also the number of multiples. It's pretty cool, pretty neat. So you get about 40, right? And is that correct, right? You get 1 to 40, which is 40 minus 1 plus 1, right? You get the numbers. You can map you have this range of numbers, 1 to 40. That you can multiply by 5 to get this mapping. And okay, So you divide, you take the floor, right? If it was 2001, obviously you don't have enough to get to 2005. So then, right, so you take the floor. So you can divide by whatever this first number, divide by this one of these, and take the floor, and that gives you the number of multiples. Now what's interesting about that is there's a couple details there. The first thing is they're saying they want to calculate the sum of all these numbers that are evenly divisible by at least one of these. Okay. So you can take, because it's the sum, you can divide by 5, get this. Now you can consider this range of numbers, right? So from 1 to 40, right? Consider this range, and there's a nice sort of number theoretic summation from all the numbers 1 to n, which ends up giving you n times quantity n plus 1 total quantity divided by 2, or n over 2 times quantity n plus 1. And that works by just, if you take 0 plus 1 plus 2 plus 3 plus ... plus, let's go, n minus 3 plus n minus 2 plus n minus 1 plus n. And you combine these, you get n, actually, no, not this one, get rid of the 0. And you combine these to n plus 1, and then you say n plus 1, n minus 1 plus 2, n minus 2 plus 3, throw 4 in there, and then n minus 3 plus 4. All of these end up being n plus 1 plus n plus 1, etc. And then you notice, because you've paired everything off in this sequence, you end up with n over 2 of them, right? Assuming you have an even number of them. And so you have n over 2 times n plus 1. That's when you have an even number of these things. If you have an odd number, there'll just be something in the middle, which is actually, by the way, n over 2. So if you have an odd number of these things, you can say take n minus 1, divide by 2. That's how many of these pairs you're going to have, times n plus 1, and then add n over 2 to that. And that gives you what is that? How does that work? This gives you n over 2 minus a half of, how does it, wait, is this correct? I forget, for the odd case it's a little bit special. There's sort of like a midpoint that happens exactly once. This will give you n over 2 n plus 1 minus n plus 1 over 2, and this is plus. Oh, yeah, if it's odd, then this midpoint we know is n plus 1 over 2. Is that right? Why would it be n plus 1 over 2 at the midpoint? Because we know if we subtract the element divided by 2, that's how many things can be paired off, and the pairs will still be n plus 1. The one pair that we can't pair off is got to be n plus 1 over 2, because, like, let's say if you take 5 divided by 2, you'll get 2, but really 3 is in the middle, right? 1, 2, 3, 4, 5. Yeah, I forget. I'm not sure exactly how you would show that it's necessarily n plus 1 over 2. That's directly in the middle, but if you add that middle point, then you'll notice they cancel in the odd case, and you still get the same value. So there's a neat little sort of quick proof. There's an inductive proof too for the same thing, but basically the sum of I equals 1 of I to n is going to give you n by n plus 1 over 2, and you can use this to quickly determine something like the sum from 1 to 40 is going to be 20 times 41, which is 8,020. 20 times 41, yeah, it's 8,020. Yeah. So you get 8,020, right? So you can use that formula and then so now for each of these multiples, you can use that formula, multiply by the multiple, so get the sum, multiply by the multiple, and then add those together. Now the problem here is that all of the common multiples you have double counted. So you've got to remove all of those. And the number of common multiples, since these are coprime, you can just multiply 11 by 17, get that number, and then all the multiples of that number are the common multiples, the ones that are that you're double counting. And I think that's all you need. Let me think about that for a second. I think there is one last detail. If it's divisible by 17 or 11, all the common multiples, which, yeah, no, that's correct. That's correct. It's, yeah. For some reason I was thinking about if you're multiplying repeatedly, but you're actually adding. So it's all those multiples, right? So then you can perform the same operation to get all the sum of all the things that you've double counted, and then subtract that instead of adding it, right? And that's it. Then you're done. It's pretty interesting. Pretty interesting. And you also, right, if the range is, now there is one more detail here, which is if you get 0, right, 0 times 0 plus 1 over 2 is just 0 again. So it'll also work for this case. So yeah, so we'll code this up. It should end up being, so I think I could do this right in here. So we have ABC, right? And we're gonna say math floor to int of A over B, AB. We can even use this percent, right? A divided by these things. We can go we'll use a let, I guess. Z B times C, and then we'll say not sums, but ranges or multiplicities, or just could do it this way. We could destructure I want to say like A prime or alpha, beta, gamma. Let's say. Just use that terminology of map this function of A to, it's going to be over the sequence of B, C, and Z, right? So we're going to map this function and here, destructure, and then we're going to say sum, we're going to return a sum of, it's going to be B times, there's another function here that we want to use, which is what do they call this? It's natural sum, I don't know what you call it. N choose 2. N plus 1 choose 2, or this guy has a name. Sum or S. I don't know what to call it. We'll just call it special, just sum. don't know if sum has a special. It doesn't. Neat. So you can use sum is going to be a function of n, and we return n times increment n divided by 2. Right, n times increment n, excuse me, divided by 2 as a function. And finally we say multiply b times sum of alpha and c times sum of beta, and finally negate z and sum of gamma. Alright, that's looking, it's looking like we probably have too much going on here. Alright. Alright, well, I thought it was going to be super concise, but I guess not. I guess not. It's alright. It's okay. Yeah, a little more involved than I'd like to be. But really interesting problem. And we can write our let like so. This is z alpha beta gamma. We're going to have this map here. The sum. Sum is going to be this function. I actually kind of prefer to put this on the same line. It's fine. Oh, that's probably. Right, this could be on the same line, given it's just a math function. And this is what we want to return at the end of it all. There we go. Okay, yeah, I was missing some parentheses here. But then we sum over, there's this b times the sum alpha, and then c times sum beta, and finally negate z times sum gamma. And that's what we want to return. Okay. Got it. I don't know. Wrong number of arguments. Core int compiling no source path. Oh, that's my mistake. Hey, oh, close but no cigar. What happened? What happened? 10 to really? What did I do wrong? What happened? No kidding. No kidding. Also, I probably could have done something with like a zip map, not a zip map, but some function to handle each of these pieces. You see how they kind of follow the same pattern, but the last one having a negation, it kind of makes it a bit awkward. All right, hold on. What does this do? What does this do? Let's use this use case here. Dang, man. Sad that I done goofed. Big divide. The Big Lebowski. The Mike Lazowski. Was it Mike Lebowski? Mike Lazowski. The old Shmagoo and Shmagagi. Alright, how do we do? How do we do? How do we do? Okay. Alpha, beta, gamma, 18, 15, 0, 23, false. Where, what do we get for each of these things? What happened? All right, so I'm aware that 369, that 3 times 5 is not above I'm aware that 15 is outside of 10. So I have 3, 6, 9 and 5, 10. Now is it inclusive or exclusive? Under n, we've got to do. Oh, okay. Gotcha. Gotcha. We'll just do that real quick. Okay. A little different than what I was calculating. Okay, got it. Right. Got that feeling. Got that impression. Okay, that ought to do it. A little disappointed it took me so many tries. Oh, come on, man. Really out of range. What? Are these not? Oh, duh. How do you do big int? Oh, each of these pieces need to be big int. That's why. All of this needs to be big int. Maybe not this one, but this one doesn't need to be big int. Well, maybe it does. I don't know. I'll do big division, and then how do we use big int in? All right, big int Clojure. Of x. All right. So these are all big integers, and then this is a big int, big int. All the things are big things. The biggins. These are also big. Big boy. Big boy. Invalid token. Nice. Nice. Looking for this guy. So Clojure docs is actually not what I thought it was. I thought Clojure docs was documentation by Rich Hickey. It's actually community based. I'm not aware. Now, arbitrary precision. So I want arbitrary precision division. That's what I'm looking for here. Somewhere in here, we have this. What about multiplication, yeah? Arbitrary precision, okay. Precision. So what's interesting is product of numbers with arbitrary precision, some arbitrary precision, this decrement with arbitrary precision. Looks like division doesn't require arbitrary precision, which seems weird to me, but I guess it doesn't matter. I guess it doesn't matter. I guess that it does not matter. Seems a bit odd, you know? It does seem a bit odd. Of course. One more time. And we'll grab this one for good measure. True and true indeed. True and true indeed. Let's see how it goes. Let's see how this goes. Oh, okay, nice, done. I don't know how I missed it. The arbitrary precision. I think I kind of knew it, but for whatever reason forgot or missed or whatever you want to say, whatever excuse I can come up with. Yeah, we got there. Yeah, pretty interesting problem. Definitely an interesting one. Thought that was cool. Neat. Definitely neat. 6 years ago, I solved this this project Euler problem. Probably even longer than that. Over 6 years ago. Probably probably even further back than that, 6 years ago. Probably even further back than that. Probably further than 6. Could have been like 7 or 8. Because my friend introduced this to me while I was at university. I was studying, and I solved the first problem like right off the bat, very quickly. I think there's a timestamp on when I actually solved it. I think it's even further. I think it's like 8 years ago I did this. Man, that's a long time ago. It's like 19 at the time. boy. Oh man, wouldn't it be nice to be in 19 again, 18 again? Know all that I know and be 18 or 19. Oh, that'd be so great. You can't think like that though. It'll make you cry, you know. You don't want to do that. I don't know. It's not how it works. It's not how it works. Never will be how it works, and you got to go to theology to think about it. You really want to know why. Yeah, I mean, I already know why, but there's no. You gotta have peace. You gotta shoulder your burden. Shoulder your burden with grace, the way God intended. Don't be thinking like that, you know. Screw yourself up doing that. So let's see, how did other folks do it? Alright, AQP. Okay. So decrement A, got it. I said let X be, so there's a sub, okay. Okay, so they combine this function with this. Yeah, that's interesting. So I did this mapping, and then I could have mapped. I probably should have mapped some. Yeah, I didn't really think of that. I should have this alpha, beta, gamma. I could have done that better. You know what I should have done? I know what I should have done. Let's do it this way. Let's take the sum, throw it up here, and let's take this alpha, beta, gamma. Map. We're gonna big int this thing. Then we're gonna sum this thing, right? And then we're going to multiply by the sum by BZC. There we go. That's better. And now we can say just alpha, beta, subtract gamma. That's a lot better. Right? You can do it this way. Mo better. Mo better. That's what that is. Mo better. Mo better. There we go. Let's give that a shot. Okay, I don't know what I did there. I managed to. What I did. I don't know what I did. True, sweet. There we go. I like that. I like that better. Mo better. A little more concise, a little more of like what they had. You could also just put decrement A right here and put multiply BZ here. Get rid of those two lines and really condense this. Then you'll get something a little more like this. Yeah, that's interesting. Interesting. Okay. 5 lines. Could be 5 lines. Alright, let's do that. Let's make it 5 lines. Let's make it, well, you can make it 1 line, but you know, let's do this. And then wouldn't typically write it this way. Just because they had 5 lines. And I want 5 lines too, man. There we go. Got him. Got him. Not too shabby. All right, moving on. You get the idea, though. It's pretty straightforward. The logic here is not particularly difficult. Like I said, it's the sort of the easiest problem on LeetCode. Oh, it's time for me to go to bed. I ignored the alarm because I really like this problem and I wanted to look at it and solve it here. I was looking to like solve it very quickly, but kind of tripped up a bit. But yeah, this is kind of a somewhat concise answer here. Get the sum function, and then you can destructure a mapping of. You could even use. I was thinking you could also use like a threading macro here to make this a little bit better, but this is okay. This is fine. The multiplication can happen whenever, I guess, or should happen at the end, and you could just this. You could use it. You could use a threading macro here. I think start with this function. I think, and then thread to floor, begin, sum. And then this guy. Yeah, that works. The threading macro here would be good too. Make that simpler. And then map this over these 3 values. And then add the first 2, subtract the last one. And you're on your way. Very interesting question. Interesting problem. Alright, so palindromic numbers. Another medium. So we've got 3 more hard problems left, which the hard problems seem to take me days potentially, where the mediums and the easies kind of take me a few minutes. Palindromic number is a number that is the same when written forwards or backwards. 399 14341. Write a function which takes an integer n as its only argument and returns an increasing lazy sequence of all palindromic numbers that are not less than n. The most simple solution will exceed the time limit. Oh. Uh-oh. Can't use a simple solution. I was going to say there's this this solution. This is, I think, the only... Oh, no. Yeah, this is kind of a funny thing. You get the first few palindromic numbers, but there are a lot of palindromic numbers. It's a lazy sequence, right? Increasing lazy sequence of all palindromic numbers that are not less than n. Not less than n. Meaning they're all larger than n? Oh, well, that's interesting. A lazy sequence. Whoa. So you take 26, they're not less than 0. I'm thinking you want to use some kind of a reduction. Now what's interesting is this does give you the palindromic sequence. It gives you a part of the palindromic sequence, but it doesn't work up to a certain point. Generating palindromes, huh? Interesting. Take the first 16 that are greater than 162. I don't know. I'm not exactly sure how to generate palindromic sequences or palindromic sequence. That's a good question. Probably. You know what you could do, right? The naive solution is just keep adding to the number and checking if it's palindromic. But they're asking for some very large values here, right? First 200, 6,666 after this very large number. So that's, yeah, it's extremely inefficient approach. You kind of want to try to figure out a way to actually generate the palindromes. What you could do in theory is create like a set. That's kind of bad though. Like, starting from some number, and you can keep increasing the value, and I guess copy the mirror across. No, that's not really good. You could take the starting point, take the first half of those numbers, copy it across to get the mirror, to get the palindrome. That'll be the first palindrome that you want to think about, I guess. If it's less, right, and then you want to, I guess that's the starting point, gives you the starting point for your number, and then you want to just keep multiplying across. The problem is if you have, well, if you have an odd number, then you keep the midpoint. So, oh yeah, if you have an odd number of digits, you keep the midpoint. But you copy across everything to the left of the midpoint, to the right side, and then you just keep incrementing the initial number they gave you, and copying across, and then yeah. So you get your initial starting point, copy across to get the next palindrome, and keep incrementing the initial number they gave you, and keep copying it across, and you keep doing that to generate all the palindromes that you're looking for. That doesn't seem particularly good either. I don't even know if it's correct, but it seems a little bit better. You can definitely do that to get the first, 666. And obviously you filter out the ones that are too small. All right, because in some cases when you copy across, it won't be big enough, the number, whatever it is. It's always got to be at least as big as this sort of first few digits copied across the midpoint. But it could never be. That's kind of interesting. You could have, 1 and a whole bunch of zeros, and then you end up with, like, if you have 1,000, you could have 1001. Excuse me. But no, that's necessarily the first palindrome, because and it's larger always, because the first palindrome that's larger than the value you gave has to be at least as big, has to be larger than the first few digits that you see. And then if it's larger than those first few digits, and if there's a smaller palindrome, then that means you match those first few digits, but you're also, then it's something that matches those first few digits, but is also smaller. Matches maybe the first one, it has to match at least the first digit. The other digits doesn't necessarily need to match. So actually you could start with, well, no. It does need to be larger than all of those digits. At least as large, right? Kind of conflicted about that. It has to be at least as large as all of those digits all the way across, but how do you... thinking if the digits on the left side are smaller, well then you're not big enough. If the digits on the left side are larger than the ones on the right side, then, oh yeah, then it's possible it's not the first. Well, no, but then, no, but then you need to be larger than the ones on the left side anyway. So you've got to keep increasing. You could be smaller. You could be too small. But you can't be too large. It's not possible. Yeah. Right. Being too far past the starting point, meaning there's some palindrome in between the value you were given and the value produced by taking the first half and mirroring it over to the right side. If there's something in between there, well, you only have two cases to consider, right? You have the case where the mirror to the left is larger than the mirror to the right, and so you end up further above you're starting further above the sort of minimum, which there would have to be something in between, but it's not really possible for there to be something in between, because whatever would be in between would need to have the same at least the first few characters on the left side. Have the same mirror on the left, at least, and then that would imply if any of those characters are incremented, then it doesn't matter what you have on the right side, because those values to the left are orders of magnitude larger than the values on the right. And then if you have, then you can't have anything smaller. So yeah, so that's impossible in that case. And then the other way around is if it's the mirror values from the left side are smaller than what you would find on the right, so they sort of overwrite with smaller values, but that means you're just below the starting point, and then in which case you're fine as well. So yeah, that's the proof. So you're always good to go if you do it that way. Interesting. But it's definitely, yeah, should be sufficient then to do it that way. That's interesting. A little less than naive. Still kind of a simple algorithm, but definitely kind of somewhat naive, I guess. Should be okay. We'll try that out later. So yeah, thank you for watching. I will talk to you all soon. Have a good rest of your night. Tomorrow, I think I'll probably start pretty early, and yeah, just try to crank out as many problems as I can tomorrow. See how far I get. We're getting very close to the end, which is kind of interesting. I don't know how many more problems. I'm gonna check the problem list again, but yeah, we're close. We're getting there. We are close. Just refresh that. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It looks like 15, 16 problems. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 problems. And 3 of them are hard. Most of them, everything else is medium, easy, elementary. So 1, 2, 3, 4, 5, 6. 6 of these are sort of mediums, which shouldn't take us too much time. The easy elementary ones should be very quick, and then the hard ones, that could take us some time. So I'd say this probably won't get done next weekend, but we'll probably be done with this problem set. I think by this time next week should be done. These the hard ones could really can hang me up for a while, and have hung me up for a while. Not all of them, but some of them are just way harder than others, and really find it exceedingly challenging. Although I'd say on average the hard ones are not that bad, but I'd say a couple of them really hung me up, a few of them. And then in terms of time, these are the ones I don't anticipate will be so difficult. So yeah, we're getting close. We'll make pretty good headway, I think, tomorrow. I don't think we'll finish the whole set, but we'll get probably half the problems done. And then yeah, this time next week we should be completed. Those hard ones can really, like I said, they could take days, so potentially. So we'll see how it goes. But I don't think it'll be that bad ultimately. don't think it'll be that bad. But yeah, thanks for watching, and talk to you soon.